Hello and welcome to the second video in this series on waves. Today we're going to look at how to label a frozen wave. One of the things you would have to be able to do at GCSE is you need to be able to look at a diagram of a wave and identify the various parts. So the parts that we're going to look at is we're going to look at where a peak is. We're going to look at where a trough is. We're going to look at how you would label the amplitude and what the word amplitude means. And we're also going to look at how to identify where one wavelength is and what wavelength means. Frequency is something else you would need to be able to identify in a diagram, but I'm going to do that in a separate video. So we are not going to look at frequency today. So before we move on, I think it's really important that we recap what we did in the last video, because knowing what we did in the last video is going to help you with what we've done in this video. So on the screen, I'm going to put up a challenge grid, and I would like you to pause the video for 30 seconds or a minute, depending on how hard you want to challenge yourself. And I want you to answer as many of those questions as possible. So we're going to start by looking at the peaks and the troughs. And before we're going to do that, I'm going to have to draw a wave. So in the last video, we talked about what a wave was. And we said a wave is produced when an object oscillates. That means moves forwards and backwards. So I'm going to draw just in the top here, I'm going to draw an oscillation. And this is what we call a frozen wave, because in reality, a wave is moving all the time. But in order to label it, we've got to freeze it in place. So it's like as if we've taken a photograph of that wave. So this line that I've drawn here shows the direction of energy transfer. So that the energy is going to move from point A and it's going to move and be transferred to point B. This line is the flat line, and it represents what we call the line of zero disturbance. It's when I showed in the last video, I showed you that we could generate a wave by having water in a tank and then moving an object up and down, and that would create a wave. So this line here, this line of zero disturbance, is when there's no wave produced. So as if the water is just still in the tank. Now, I'm going to draw on the frozen wave. So imagine we're moving the object up and we're moving the object down and up and down and up again. Now, this part of the wave here is the positive part of the wave, and this part of the wave here is the negative part of the wave. All waves have got a positive and a negative because you have to move an object up and then we have to move it down and then back up again. And that's one complete wave cycle. I'm going to label this wave for you, and we're going to talk about this wave, and I'll show you some sort of examples of it in this area of the board here. So this part here, when the wave very first starts, the line of zero disturbance, we're going to call part A, and then part B is going to be here. That's when we're at the very top of the wave. Part C, when we're back down to the line of zero disturbance. Part D at the bottom of the wave. E at the next one. F, G, and H. Just check I haven't missed any. So A, B, C, D, E, F, G, and H. Okay, and I suppose this part here would be I as well. So we've got our frozen wave labeled, and these letters I'm going to use when I'm talking about this wave. Okay, so the first part of this wave that we're going to look at is the peak. So what is the peak? Now this is a pretty obvious one. If we take a mountain, okay, here's a drawing of a mountain. I'm going to put some snow on the top. If a person was going to climb this mountain and they got to this point here, this would be the peak. So the peak is the very top. All right, when you get to the top of the mountain, you stick a flag in it, don't you? You've reached the peak. So in this diagram here, B is a peak and F is a peak. The next part of the diagram that we need is a trough. So if I was going to draw a trough is something that it's just like a hole in the ground almost that you could sort of like put stuff into. So when I think of a trough, you think of almost like something like an area where you would put some food into and an animal would eat out of it. That's what we call a trough, like in here. So the trough is the bottom part of the wave. All right, so this is part D, and part H, that is your trough. So far, when we're drawing our waves, we've got a peak, and we have got a trough. Remember, we need that line in there, the zero displacement. Okay, the next thing that we need is we need to look at what the amplitude is. Now, the amplitude is the distance between the zero line. So I'm going to draw in my zero line, and I'll properly label it. So here's the zero line. So the amplitude is the distance between the zero line and the top of a wave, so the peak, or the trough of the wave. Now, it's important to remember, so I'm just going to label this as 1, 2, 1, 2. Remember, these are positive numbers and these are negative numbers, because this is zero disturbance and this is when it's been positively disturbed and this is when it's been negatively disturbed. So if I'm going to draw on my amplitude, I'm going to start with a wave that only goes up to the 1, and then it's going to go down to the 1 and back up. So there's my first wave cycle. So the amplitude is from this line of zero disturbance, and we have to make sure that we draw all the way into the peak. So that is the amplitude, okay? And we could also draw it here as well. It's the same height. I should say the same distance. So the amplitude is the distance between the line of zero disturbance and the peak. Now I'm just going to take these off so that I can do something else. I'll cover a quick misconception first. I've seen this diagram shown before in an exam question, and it said which one of these arrows is the amplitude, and a lot of people go for this arrow. You have to remember, it's you draw in the middle line, the line of zero disturbance. It's from the zero disturbance to the peak. That is 2 amplitudes. Okay, so the amplitude is actually just a measure of the intensity of a wave. So if I was to draw, let me draw a light bulb. So let's pretend that this is a representation, this wave, of a light wave. Now I'm going to put my little light bulb in. Now at the moment, it's giving out that much light. Now I could draw another wave for another light bulb. Let's say I've got this on a dimmer switch and I make it twice as bright. So this is, I've got my lines up, twice as long. So this light is twice as bright. So what would happen to the amplitude is it was at 1. I'm now going to increase the intensity to 2. And I'll do it in the negative as well. So you can now see that my amplitude has gone from the line of 0 to the peak is double what it was. And we can see that this light bulb is twice as bright. So the amplitude just represents the intensity of the wave. If this was a sound wave, now this is drawn as a transverse wave, and we'll explain that a little bit later, but if we can represent it as a transverse wave, but in reality a sound wave is longitudinal. But if this was a sound wave, one that would be twice as intense would be one that was twice as loud. So for instance, this would be a quiet sound, and then this will be a much louder sound, okay? So quiet and loud, and easy, okay? And we could, all different waves. If this was a water wave, obviously the height would just be, it would be carrying twice as much energy. So that's it. Right. So the final part of the wave that we have to discuss and we have to be able to identify is the wavelength. Now, wavelength is represented using this symbol. This is it's the symbol lambda, okay? And it's just, personally, I think it looks like a coat hanger. There's a coat hanger, but without the bottom part. So lambda, as I say, I'm going to use because it's shorter than writing wavelength each time. So the wavelength, the word length is very important. It's measured in meters. So that's why it's a wavelength. And it's the distance between 2 equivalent points on a frozen wave, and 2 equivalent adjacent points, the ones that are next to each other. So the easiest one to spot, if we look at this very wave at the top, is 2 equivalent points. That means they're the same. It's dead easy. It's B and F. So if we're going to just zoom those out, okay. So we've got 2 peaks. It should be the same height. There we go. So we've got two peaks. So we've got B and there, and we've got F there, and we're going to draw a line between them, straight line. And if you notice that my arrowhead goes exactly to the center of the peaks, that's really important. That is one wavelength. You could have exactly the same, could be between D and H. They're two equivalent points that are adjacent. They're next to each other. All right, so we'll zoom that in, like that and like that. So these are the troughs. So we've got there to there. Draw that line between. Notice my arrowheads touch. That's a wavelength T. The trickier one is along this center line. That's where things get a little bit trickier. So a big misconception that students often label the wavelength as between A and C because they look like they are equivalent points. They're both on the zero line, therefore they're equivalent. But in reality, that's not true. I'm gonna show you why. So I'm gonna draw a terrible wave diagram. Let's try again. I'm gonna draw a wave diagram here. Now we're going to imagine that this is a mountain again. And this line of zero disturbance is our sea level. We'll carry on the next wave. Now, one wavelength is the equivalent of one wave cycle. So if we've got a little person here, and this person is a mountaineer, they're going to be climbing this mountain. All right? So they're on the way up the mountain here. They're going forwards. Put a little hat on them to represent which way they're going. So they're going forwards. And you can clearly see that they're going up here, they get to the top, they stick their flag in the peak, and then they're coming back down here. So we'll put another leg on. I apologise for this drawing, not the best. There we go. All right, they're on the way down the mountain now. So it's quite obvious from this diagram that, look, when you are climbing the mountain, you go up to the peak and you come back down. This is not the equivalent point because here you're going up the mountain and here you're going down the mountain. This is two sides of a mountain. They are different points. To get back to here, back to the same point, you would have to go right down into the trough and then back up to here, actually, where you'd start to climb the mountain again. So I'm going to take this one off. I'm going to put this person in because by now they're ready to climb the next mountain. The other one was still part of the same mountain. So the equivalent point is not between A and C, it's between A and E. The next time they are on the beginning of the mountain. So they've done a full wave cycle. They've gone up the mountain, they've got to the peak, they've gone down, they've got to the bottom of the trough, and they're back up to start the next mountain again. One wave cycle between there and there, one wavelength. So if we look back at our original graph, we should be able to label this totally now. So we've got our peaks. Our peaks are B and F. We've got our troughs. Our troughs are D and H. We've got our amplitude, and that's from the line of zero disturbance to the top of the peak, or from the line of zero disturbance to the bottom of the trough. And we've got a wavelength. So we could say a wavelength is between B and F, or it's between D and H, or it's between A and E. In the next video, we're going to look at frequency, where it's really important that you can take one of these frozen waves and you can distinguish how many wavelengths there are. So I'm going to add some questions that I'd like you to try and answer, and I'll see you in the next video where we're going to look at frequency.